this brings us to the modes of heat transfer. So, we have looked at these in several courses earlier. So, we know that the modes are conduction, convection and radiation. So, we will go through those just so that we sort of refresh ourselves as to what they are. So, when you have talk of conduction, we are talking of energy transfer between molecules. So, the molecules, for example, in a solid, they cannot move out too far away, but they can vibrate and transfer energy to neighboring molecules. In a liquid or a gas, they are free to move more. So, the Fourier's law of conduction tells us that the rate of heat transfer q dot or q prime is given as minus Ka into the gradient of the temperature. So, dt by dx. Of course, we need to look at each of these, but before that let us just look at some values of K. So, we see that for metals K has a pretty high value. So, K has a value of about 100 watts per, there should be a dot here, meter Kelvin. For non-metallic solids it is of the order of 1 to 10 watts per meter Kelvin. It is of about 0.1 to 10 watts per meter Kelvin for liquids, about 0.1 for insulators, and for gases it is very small, it is of the order of 0.01 watts per meter Kelvin. You should remember that this is not a millikelvin, this is a meter Kelvin. So, that is the kind of values we see for different substances. So, clearly if you have a metal, you have a lot of conduction through it when there is a temperature difference, and not so much in the case of liquids or gases by conduction. So, when we look at say one dimensional heat transfer, we see if you have a block, for example, let us say you have a block of this kind, let us say this is a block, the temperature at this wall is some T1, the temperature at the other wall is some T2. So, if T1 is higher than T2, then we have heat transferred from this side to the other side from T1 to T2, and the gradient is given by dt by dx. So, if this direction is x, we see that dt by dx is the slope which is negative, and the heat transfer or the rate of heat transfer would be considered as positive. And in the similar case, what we see is that if you had a slab like this, if the temperature here was T2 which is higher than T1, then this is T2 and this is, let us say, T1, this is x. What we see is if the slope is positive, so if dt by dx is positive, so dt by dx is in this case, this is T2 minus T1 by x2 minus x1. So, if this is positive, then we see that heat is being transferred in the negative x direction. So, we have that minus sign over there to account for this. So, we have the minus sign over here to account for that. What we should also keep in mind is what these things mean. So, for example, if I have a slab of this kind and let us say this is the x direction. So, if I am looking at heat transfer in the x direction, I am looking at conduction. So, this is minus K, K is the thermal conductivity, A is of course the area perpendicular. So, if I am looking at heat conduction in the x direction, the area of course is this area, okay, and dt by dx would be the temperature gradient between this and this. So, we need to make sure that we understand which area we are looking at. So, we are looking at the cross sectional area perpendicular to which heat is being transferred. In the case of solids, conduction is obviously one of the biggest modes of heat transfer, but in the case of flowing media like liquids and gases, we have convective heat transfer because there can be a velocity for the substance and the substance can flow. So, in that case the rate of heat transfer q dot is given as the convective heat transfer coefficient into the area into the difference in temperature, which we call as the Newton's law of cooling. In this case there are several things we need to keep in mind. The units of the convective heat transfer coefficient is essentially Q dot divided by area into delta T. So, Q dot has the units of watts, area has the units of meter square, delta T has the units of say Kelvin. So, this has units of watt per meter square Kelvin. In contrast, when we looked at thermal conductivity, it had areas of watt per meter Kelvin. So, we see the units are different. So, if we have a surface like this which is hot, and let us say we have some fluid which is flowing in this direction. So, the temperature of the surface, let us say, is some Ts. The temperature far away from the surface is, or the temperature of fluid which is coming in undisturbed by the surface, is what we call as T infinity. Then we see that the heat transfer or the rate of heat transfer is given as H into A into delta T. So, over here that delta T would be if Ts minus T infinity if Ts is greater than T infinity. So, this is the amount of heat transfer given by Newton's law of cooling. In this case, what we see is that the area is the area which is shown over here. So, we have heat which is being transferred when fluid is flowing over this area. Whatever is the area over which fluid is flowing is the area which comes into our formula over here. And the value of this constant, so to say, is actually varying depending on the circumstances we have. So, if you have natural convection, for example, if you just have a plate which is hot, then the air which is in contact with that plate or water which is in contact with that plate will have a lower density because it is hotter. So, it would rise, because of which some other stuff will come below it, and you would have what is called as natural convection going on. In the case of gases, if it was air above a hot plate, the natural convection happens, because of which we have a convective heat transfer coefficient of about 5 to 25 watt per meter square Kelvin. In the case of liquids, it is much higher, about 50 to 1000. If we now have a fan to blow the air or the liquid over this plate, we can get much higher rates of heat transfer. So, we see that we can get a rate of about 25 to 250 watts per meter square Kelvin in case of gases, and we can get much more, about 20,000 watt per meter square Kelvin in the case of liquids. And we see even higher rates of heat transfer when we have a phase change. So, for example, if I have water on a pan which is boiling, I am sure all of you have tried this at some point at home. So, you have like a tawa which is really hot, and you splash some water on it and it boils and makes a sound and goes away. So, in those kind of cases, you can get a very high heat transfer rate of up to say 1 lakh watt per meter square Kelvin. So, if you want to cool something really fast, that is a much better way of cooling it, rather than just letting it out in the air on its own or using a fan to blow air across it. The third mode of heat transfer is of course radiation, but before that a quick question for you. What are these examples of? Are they free or forced convection? So, you should take a moment to think of all of them. So, the first one, because it shows a hair blower which can be used for drying hair. So, what is it an example of? So, you should possibly pause for each of them and think about it for a minute. So, in this case what we see is that we have a fan and a motor inside, because of which air is being blown out. So, it would be forced convection. So, B shows the radiator of a car which is used for cooling the engine of the car. So, again, do we have forced or natural convection? So, if you have looked at one of these things closely, what you would see is, again, there is a fan behind it usually to blow air across it. Even if there was not a fan behind it, when this vehicle was moving, because it is moving in air and this vehicle has a velocity, there would be flow which is being pushed past it because of the vehicle's motion. Okay, so, we would have forced convection in this case. C is something which people in cold regions are likely to have seen. It is a room heater. And again, the question is it free or forced convection as far as heat transfer from this heater to the rest of the room? And what we would see is, if it was in a still room, you have convection because this is hot and it heats the air around it. What you can also have is radiation between this surface and the rest of the room. This is also something which you might have seen if you have opened a computer or something like that at some point of time, or a TV or some stuff like that. So, we have electronic chips and we have what are called fins, and the idea of this is to increase the surface area available for heat transfer by putting many of these instead of having just a flat surface. So, in this particular case where we see there is no fan or anything like that. So, we have free convection, which is natural convection, because these plates would become hot and they would heat the air which is next to it, which would then move away and bring in fresh cool air which can then transfer out more heat. And the last example here is again taken from one of the books, where we see what is called as a Schlieren photo, which can show you density gradients. And what we see over here is natural convection because of a person standing in a cold room. So, our body temperatures are regulated. So, it is close to 37 degrees centigrade. If you are standing in a room which is, let us say, 25 degrees centigrade, so your skin's temperature is much higher than the surroundings. So, you set up natural convection currents which can be made visible by using various techniques. So, we see that there is our head, for example, gives out a lot of heat. So, you see a lot of convection around there. Clothes trap in a lot of heat, so you do not see so much convection there, but exposed parts of the body like the face and the hands and so on give out more heat, which you can see. That brings us to this third mode of convection, which is radiation. So, in the radiation we have transmission of energy as electromagnetic waves in space, and we can find out the radiation from the surface. So, Q dot, which is the rate of heat transfer, is given as epsilon into sigma into A into the temperature of the surface to the power 4. Again, the units is in watts. Sigma stands for the Stephen-Boltzmann constant, which has a value of 5.67 in 10 power minus 8 watt per meter square Kelvin to the power 4, fairly strange units, which is something we need to remember. And epsilon denotes the emissivity of the surface. So, what we know is that a black body is completely black, is the best emitter and the best absorber of energy. So, if you have a surface which is not completely black, how well does it behave compared to an object which is black is what is given by the emissivity. So, the emissivity for non-metallic surfaces is about 0.9. When you have a non-polished metallic surface, so essentially a rough metallic surface, you can have the emissivity values are typically of this order, 0.6 to 0.9. And if you have a really nice and shiny, smooth, polished metal surface, the emissivity is very low. So, if you want to get rid of a lot of heat, you have a hot object, it is useful if that object is non-metallic as far as radiation is concerned. If it was metallic, it is useful if that object has a rough surface, because then it would radiate out heat a lot more. But of course, in most cases what we see is that the heat transferred would be a combination of conduction and convection and radiation. But if you were in places, for example, where there is no medium around, if you were in space, if you have a satellite there and you want to get rid of heat, convection is not going to work because there is no air around there, you are in a vacuum. Conduction is also not going to work because there is no substance around which can transmit heat away. So, then radiation is the only way in which you can get rid of heat, and you would want to have a surface which has a high emissivity if you are trying to get rid of heat. Now, we can look at how the emission from a gray body looks like. So, emission from a body which is not a black body, but the ratio of the emission at any wavelength is the same, is what we call as a gray body. So, what we see is that if it has an emissivity of say 0.7, then the ratio of this to this would be 0.7, ratio of this to this would be 0.7, and so on. At all wavelengths, the ratio would be the same. So, emissivity is the ratio of the emission from a gray surface to the emission from a black body. And what we can also look at is spectral emissive power, which is the emission at a given wavelength or a small band of wavelengths. We have in our usual discussion on heat two other terms which we need to think of what is called as specific heat and what is called as latent heat. We will also define these in the context of specific heat. We will discuss in the context of ideal gases later on, but for the time being what we see is a specific heat is the amount of heat you need to give per unit mass per unit change in temperature. So, for example, if I have a block which is of mass which is 1 kg and I want to change its temperature by 1 degree centigrade, how much heat do I need to give such that its temperature goes up by 1 degree centigrade. So, we know that this amount will be different depending on what substance it is. For example, if I have 1 kg of water and I want to change its temperature by 1 degree centigrade, I need to give a lot more heat than if I had 1 kg of air and I wanted to change its temperature by 1 degree centigrade. So, we see that it depends on the substance. What we also will see later on is that it may depend on the temperature. So, if I want to change its temperature from 15 degrees to 16 degrees, it would be different from the amount of heat I need to give to change its temperature from say 90 degree to 91 degrees. Okay, so that is also something which we will see. The latent heat is the amount of heat we need to give in order to change the phase of a substance. So, if I have 1 kg of say ice, I want to convert it into 1 kg of water at the same temperature. The amount of heat I need to give is what we would call as the latent heat of melting. It would be the same as the latent heat of freezing. If I had water at 1 kg of water at 0 degree centigrade, I want to convert ice at the same temperature. The amount I need to remove is what would be the latent heat of freezing. Similarly, I can have the latent heat of boiling or latent heat of condensation, which is amount of heat for a unit mass in order to change phase at the same temperature. So, this again would depend on the substance which we have. So, before we continue, we have 2 more questions here for you to think about. First, whenever an object receives heat, does its temperature need to increase? Will the temperature increase whenever an object receives heat? So, you should possibly pause and think about this for a moment. The answer of course is that it does not have to be the case. We said earlier also that if I have ice, I give it heat, it becomes water which is at the same temperature as the ice if I just give it a small amount of heat. So, what we see is whenever it receives heat, its temperature does not need to increase, it may increase or may not increase. The second question I have here is, if the temperature of an object increases, does it mean that there was heat transfer to the object? So, I have some object, its temperature is some value. After some time I measure its temperature is higher. Does it mean that heat was transferred to this object because the temperature increased? So, you should think about that too. The answer of course is that it is not the case, because I can have the temperature of an object increased by doing work on it as well. So, if I have for example a familiar piston cylinder arrangement, if I was to have an insulated piston cylinder arrangement and I compressed it, I would do work, but I would expect that the temperature of this gas increases because I am doing work on it. Or for example, if I for example, in this room here it is fairly cold, so what I do is I rub my hands together and they become warm. I did not transfer heat to it from anywhere, but I did work in rubbing it against friction, and in doing so I increased the temperature of my hands. So, just because the temperature increased does not mean that heat was transferred. I can also have temperature increase because of work transfer, or I can have temperature of a substance also reducing because the system is doing work on its surroundings. So, what we saw earlier is that work is given as 1 W2, which is integral of del W, and when we have displacement work due to the deformation of a control volume, or deformation of a system, we have the work given as integral of PdV. In a similar way, heat is given as 1 Q2, is given as integral of del Q. So, there must be some way of writing this in a similar fashion as integral of T temperature into change of something else. We will see that this something else is what we call as S, which we call as entropy. we will look at it later on, but we will just remember for the time being that we can do this at some point of time. Similarly, we saw that the area of a PV diagram for a quasi-static process when you have displacement work gives us the work done. Similarly, we will see at later on that the area under a TS diagram for a reversible quasi-static process can give us the amount of heat transferred. We will discuss that in a lot of detail little further on in this course, but for the moment we will just say that the same way we have a PV diagram which shows us work, we have what is called as a TS diagram which shows us heat, and integral of PdV gave us work for a quasi-static process for displacement work, and integral of a TS diagram would give us the heat transferred for what is called as a reversible process when we have heat which is being transferred. So, that is where we stop at this lecture, and we will continue on the first law of thermodynamics in the next lecture. Thank you.